Vector fields. Let D be a set in Rn. Then a vector field on Rn is a function f, that is a vector function f, that assigns to each vector x in D an output vector f of the vector x. In R2, we usually write f of xy equals p of xyi plus q of xyj. Let's do a quick example of a vector field. Consider the vector field f of xy equals negative yi plus xj. And we want to draw a representation of f. This is a pretty straightforward concept. All we need to do is pick different values of xy, that is, pick different points, and find the vector associated with it. For example, if I choose the vector 1, 0, notice that f of xy is negative yi, so negative 0i, I just put 0i, plus xj, plus 1j. So at the point 1, 0, this vector field has the vector 0, 1. Just like that. And if I was at the point, say, 3, 0, then negative yi, so 0i again, plus xj will give me 0 plus 3j. So at the point 3, 0, we would have the vector 0, 3. How about at the point 0, 1? At 0, 1, we'd have negative yi, so negative 1i, plus xj plus 0j. So at the point 0, 1, we'd have the vector negative 1, 0, like this. And at the point 0, 3, we would get the vector negative 3i plus 0j. So at the point 0, 3, we'd have this vector here. How about the point, say, 2, 2? Well, negative yi plus xj will give us negative 2i plus 2j. So at the point 2, 2, that vector would be negative 2 on the x, 2 on the y, pointing up like this. And if we found a few more points, we could fill in more detail, but I think you get the idea at this point. Something along these lines. Now, one way to think about this, or to understand what these vector fields are, is to imagine maybe this is a force field. And to say a particle got shot into the force field. So this is not a vector, right? A particle gets shot into the force field. Can you imagine what would happen to this particle? If it got in here, it would probably be doing something like this, right? We can see this rotational motion in our vector field. And I'll come back to that a little bit later and then also in later videos. But let's look at another definition, just very briefly. Let f be a function of xy. That is, it's a scalar output or scalar valued function of two variables, or we could do more variables if we needed to. Then the gradient of f of xi plus f of yj, is a gradient vector field. Okay, let's just do one quick gradient field or gradient vector field. Given f of xy equals x squared y minus y cubed, then our gradient vector field is just finding the gradient. It would be the partial with respect to x, I, plus the partial with respect to y, j. So 2xyi plus quantity, x squared minus 3y squared j. There's a gradient field. Let's finish with this last definition. And we want to talk about something called a conservative vector field. So a vector field is called conservative if it is the gradient of some function, some scalar valued function, f. Show that the vector field f equals 2xy plus 2I plus x squared minus 2yj is a conservative vector field. So to do this, we have to show that f is the gradient of some scalar valued function. Now, how can we do this? I'm going to show you one way to do it. Notice that f of x is 2xy plus 2. So the partial respect to f must be this if big F is indeed conservative. And then if we do have a conservative vector field, then the partial with respect to y of little f must equal x squared minus 2y. So given this, our function could be found by doing the integral of the partial with respect to x dx. So if I reintegrate this with respect to x, we get x squared y plus 2x. Now I'm not done yet, because I have to assume there's also some function strictly of y, or at least there could be, right? Because if I take the partial of this thing here with respect to x, anything that has y's only would disappear. So if I took now the partial with respect to y of this, we would get x squared plus 0 plus g prime of y. All right, some derivative of only y's. But I already know that f of y must be this right here. It must equal x squared minus 2y. Which of course means that g prime of y is negative 2y. Which tells me that g of y must be negative y squared plus some constant. Putting these ideas together, we get our original function f of xy is this, x squared y plus 2x minus y squared plus c. And if you go ahead and take the partials of this, you'll see that you get where we started. Now, just a brief mention, because we're not going to try to draw this vector field. But an idea we want to wrap our mind around throughout this unit is, what does it mean to be conservative? This word was chosen for a reason. Sure, there's a definition that we use, but what does it really mean intuitively? And that's one of the things we're going to talk about as we go through and see some of the more advanced concepts in this section. One of the things we will see, just very briefly, is that if we have some sort of rotation in our vector field, it won't be conservative. So I'm not going to go into more detail now. I just want to plant this in your mind so that as we go through this unit, that you think about, what does it mean to be conservative?